So picking up where we left off, we came up with a definition of limit based in part upon the examples that we looked at, but I have to confess it was also based in part on what I know is coming up soon and you don't know. But you'll know it soon enough. At any rate, let's take a look at the definition that we came up with and let's see how it fits into the situation of 4 different graphs. So we need a little bit of room here. Let's get rid of that. Let's give us some graphs. And let's take a look. Let's first start with a function like this. Okay? We're interested in seeing, again, when we talk about a limit at a finite value of x, we're not talking about the entire function. We're just talking about the function at one particular point. So the question is, if I've got some function, maybe this is x squared, y equals x squared, and is it the case that the closer I get, coming from either direction, the closer I get to this value in x, do I get closer and closer, or rather as close as I want, to one particular value in the height? Well, if I do, then that height is L, and that's the limit. So for a typical function like an x squared, it looks like it's working fine. Let's try this function. We want one where it doesn't, where we want to be able to say that the limit does not exist. How about a function like this? I think we had something like this on the last slide. So let's look at this one in more detail. Now again, we're only interested right in this point. We're asking a question just about this point. The issue is, as I get closer and closer to this, does this get closer and closer to one particular height? Well, as I get closer and closer coming in from this side, it gets closer to this height. As I get closer and closer coming in from this side, it gets closer to this height. But these two heights are not the same. So whereas this has a limit, let's call this 1. This is just a suggestive diagram. Whereas this has a limit, we're going to say that the limit does not exist at 1 for this function. And then what about this intermediate case that I drew earlier? Here's the one that it's interesting to think about the definition. Okay? If I get close enough in x to this value, do I get closer and closer to one particular height? Well, the answer is yes. And here's where the but never touching comes in crucially. Okay? I actually never touch this point in the x. And so I don't really have to worry about what's going on in the y right at the point. It's just near the point that I have to make sure this is getting closer and closer to one particular height. And it is. So the limit exists here as well. Now let's try just one more to sharpen your thinking about what limit really means. We've got this function here, and right at 1, it takes on this value, not this value. So what's the situation? The closer I get to one particular value in x, but never touching it, do I get closer and closer to one particular value in the height? Well, in fact, I do. And it's this value. This value is not relevant. And that's because of the never touching issue. So think about what this is saying, because it's a little bit counterintuitive. I think none of us has trouble with understanding why this has a limit that's equal to the value at the x, the value that corresponds to the choice of x. But what's interesting here is it tells us that limit actually doesn't have to have anything to do with the value at the point. And that leads to what some people call the pencil test, which means you could cover up the point in question with a pencil. Imagine putting a pencil down on a sheet of paper that had the graph on it. You could cover it up with a pencil, And you'd never need to know what was underneath the pencil. You'd never need to know what was actually happening right at that x value in order to answer questions about limit. So, if we applied the pencil test here, again, this is just sort of for fun. I'm trying to draw in a pencil on this piece of paper. I can't tell the difference between these two graphs. And I'm doing that just to emphasize this point. The value of a function right at a particular x value doesn't necessarily have anything to do with the limit as you approach that point. It's okay if the value is the same as the limit. It's okay if the function doesn't even exist at that point. It's okay if the function has a different value at that point. In all three cases, as long as you're getting closer and closer, but never touching, that's what determines the limit. And that's a little bit unintuitive, so I just want to point that out explicitly. Okay, I hope you have a general sense for how the definition of limit fits with our intuitions in most cases and is a little bit counterintuitive in at least one situation. So now I'm going to repeat, in a sense, the very same logic that we used in a progression for finding limits at infinity. We can now apply that same basic progression for finding limits at finite values of x. Namely, we first check to see if something's a known limit. If not, we try graphing it. If not, we'll have to use 5 limit laws that will be the very same limit laws, except for a tiny technicality that we won't cover. The very same limit laws that we had for limits at infinity. And then algebraic simplification will be what we use for indeterminate cases, and the sandwich theorem is yet another way of finding particularly incorrigible limits. So let's just see how it works. Let's start with some known limits. So probably the simplest function I can think of would be a constant function. Let's suppose this was 3. So f of x is 3. And so we ask ourselves, what is the limit? And let's pick 2 for our x value. What's the limit as x goes to 2 of the 3 function? Well, the answer is 3. Namely, simply by getting closer and closer to 2 in the x, I can get as close as I want to one particular height. Now in this case, of course, I never leave that height, but that's not the point. This meets the definition of limit. I can get as close as I want to the height 3, and so the limit exists, and the limit is 3. Let's try another function. Let's try the function, so we'll just say this was f of x equals 3. Or more generally, I really could have said any kind of constant. So we'll call this general limit law, we'll write it like this. The limit as x goes towards some number of a constant function is just the constant. Okay, now let's try this function. I'm going to say that this is y equals x. F of x equals x. We want to know what the limit of that function is as x gets closer and closer to c. Well, again, the closer I get into c here, is there one particular height that I get closer and closer to along the y-axis? And the answer is yes, and the height that I get closer and closer to is also c. And so we'll just say that the limit as x approaches c of x equals c. Now the good news about limits at finite values of x is that essentially all of the basic functions that you're used to dealing with, like sine x, cosine x, e to the x, natural log of x. For all of the values where they're not infinite, like ln of x we know goes infinite when x equals 0, but for all of the other values, the limits of these functions, all of these basic functions, is simply the value at the point. It's only when we have to start combining these functions that we have to move beyond known limits. We're going to say that all of those are known limits, to the graphing, limit laws, algebraic simplification, and so forth that we covered in limits towards as x approaches infinity as well.